So, good afternoon. My name is Alberto Venturi. I am here with my colleague Jonathan Robinson to speak to you about the challenges of perception sensor for automotive vehicle. We will start with a short introduction about the WNG and the group sensor working in WNG. Then we will move to present the WNG radar model developed by my colleague, and then we conclude with some consideration about the future of radar in automotive. So about WNG and the sensor group. WNG is a department of Warwick University. It was created in 1980 by Prof. Lord Bhattacharya. And the main idea of this department, it was to facilitate the transfer of knowledge between academia and industry. To highlight this aspect, I would like to tell you that WNG is co-located with Jaguar Land Rover and Tata Motor European Technical Center. More than 800 people work for WNG in very beautiful buildings. There are some pictures of those buildings. And more than 1,500 people are trained every year, people that come not just from UK, but also from all over the world. Inside WNG, the Intelligent Vehicle Group Research made research about technologies for autonomous vehicles, with the idea to make those technologies dependable, desirable, and viable. Those research are made in modeling simulation, controlled environment, and public environments, with the idea to take advantage of the specific aspect of each one of those environments. An example of the activity of the Intelligent Vehicle Group Research is the cooperation with the Midland Future Mobility. It is a consortium that, for example, is deploying at the moment on more than 200 miles of road of West Midland infrastructure and equipment like camera, like weather station, like communication units, making available very high precision GPS signals in order to facilitate and make more safer the development of technology for autonomous vehicle and make possible the first business application of those technologies. One important aspect is for sure the work with sensor simulation and emulation. The sensor group inside the Intelligent Vehicle Group take care of the activity of the group about a sensor. People speak about the revolution of autonomous vehicle. We can say that it is a sensor-based revolution, because a sensor that allow the control unit of the vehicle to understand the world around the vehicle are very, very important. Those are environmental perception sensors like camera, radar, LiDAR, ultrasound are the interface between the real world and the automotive system. A key concept is the so-called robust sensing. So to understand how the uncertainty of the measurement that can be caused by environmental noise, unexpected, incomplete data, or the failure of one of the sensor that is installed in the car are transferred all along the chain from the sensor till the control unit, and how this uncertainty impact the ability of the control unit to take the right decision at the right moment. Some key projects on which the sensor group is at the moment working are about sensor and noise model, noise factor, data degradation, data reduction, fusion, data perception, and machine learning, of course, data quality, interference, sensor spoofing, just to give you some examples. Here we have two videos that at the moment are not starting. Okay, the first video it was starting is an example of a simulation of a camera sensor with low light, and the second video is the example of the simulation of the radar sensor. Okay. Nothing is working. Okay. One of the projects on which the sensor group is working is the WNG radar model. The WNG radar model has been developed to understand and model the effect of interference on performances of a radar. The radar modeling has been built using discretization of radar beams. We think that radar is highly important because we move toward an higher automation level, and the radar will be for sure one important sensor on the cars. And moreover, the number of radar sensor hosted on a car is going to grow more and more. Okay, benefit of the radar. The good aspect of a radar sensor for the automotive application is that it is less effective than other sensors, for example, camera, by the weather condition, because of the higher wavelengths with which it's working. It's not affected by illumination condition because the energy for the measurement is provided by the sensor itself. Can directly measure distance and radial velocity of the target because of some physical effect on the reflected beam. Can discover objects with a range till up 300 meters. Is getting relatively inexpensive. So nowadays we imagine that a number of 5-8 radars will be installed in new cars. And those radars become available also for mid-level cars, no more just high-level cars. The radar comes also with some limitation, principally related to undetected target, in particular if you think about a vulnerable load user like pedestrian. And with a difficult in target recognition. Also, when a target is detected, it's difficult for a radar to understand exactly what was this target, because always of these longer wavelengths with respect to camera that make difficult this target. There are problems also with what's called ghost target and interference. We'll speak a bit better in the next slide. With ghost target, we speak about the effect related to the multipath reflection. If we imagine one car, of course, unfortunately, it's not represented on this slide. It got lost. This is something. Okay. Anyway, imagine a radar is sending a beam hits a first target, a first car, and because this reflection is scattered in all the direction, it's possible that on his path you get another object that reflects again versus the sending sensor. The sending sensor can give the interpretation of the signal as it was a second target. Tracking technique can mitigate this effect, practically following the target over the time and see of this target change. Interference. Now I let my colleague to introduce you the interference problem and speak about the model.
Okay, thank you, Alberto. Seems we're having a bit of problems with the figures today. We did have a diagram here to aid my explanation, but it seems to have vanished. So I'll do my best. So what I'm going to talk about now for the rest of the presentation is interference in respect to automotive radar, why it's an issue. I'm then going to talk about in a bit more detail the original model we had, the model we now have after some changes we made, and then what we plan to do in the future, and that involves the interference. So I'll try to paint the best picture I can of what this image would look like. So if we had, down this area, if we had our vehicle equipped with our radar, our victim vehicle with our victim radar, and then ahead on the road we had another vehicle called the target vehicle, and we have a distance between them, let's call it R. So if our victim vehicle has a victim radar on the front of the car and our target vehicle has a radar on the rear of the car, it's possible that that vehicle's radar can interfere with our radar. Now, the reason why this is an issue, and you can see the diagrams on the right, is that the power you get from the interfering radar is a lot greater than you would from the reflections that you get from the target. So you can see the radar we have there with PR, and then below the power you'd get from the interfering radar. So because you have no reflection, you have no RCS value, and because you're only traveling one lot of R rather than there and back, you have a smaller value on the bottom, which essentially means you get greater power from the interfering radar. So two principles with this, which we're looking at, are interference to noise ratio and the signal to interference ratio. So the interference to noise ratio is the ratio of the power of the interfering signal to the noise floor. So you'll always have some noise in your signal, and we're looking at how much power the interfering signal has compared to the noise floor. And obviously if it's too far above the noise floor, that's when we might start to detect that as a signal. The signal to interference ratio is looking at the ratio between the signal that we wish to receive and the signal we receive from the interference. So you can see the leftover terms from the radar equation there, plus this GP, which is essentially represents a gain that you can introduce into your radar sensor to improve the detection. But you've got the RCS on the top and the 4 pi r squared on the bottom. So the longer that distance is to the object, the smaller that signal to interference ratio is. So just a bit on the model that we have. So the original model was in Unreal Engine 4 within the 3xe simulator that we have at WMG, and it used to work with line traces. So each beam would be approximated by a single line trace, which would produce hit points within the scene of Unreal, and then combining all the different beams, we could average them to get the position of the object. Although, as you can see from the diagram on the right, my incredibly budget radar diagram, these beams are a lot wider than a single line trace because radar beams spread out, so therefore you get a lot of divergence. So we needed to model this divergence, and I'll explain that in the slide after this. Just as a bit of extra intuition, so we get the hit point which determines the position or the distance to the object, but to determine the width, we need to use the hit points that we've got. So you'll have a number of hit points along the object, and using the angle between them, you can determine the length. Using the number of hit points, you can determine the entire width of the object. And just as a side note here, currently RCS is approximated as a cylinder, although I'll explain later, hopefully we'll be improving that in the future. Okay, that's also missing. So this was a video. Unfortunately, I can't paint a picture of a video. No idea why these have suddenly disappeared, but we'll try to move along. Okay, and again, I would have an image there. I don't know why all of my images have disappeared. So essentially, we would have a MATLAB diagram over there, which would show how we've now implemented divergence. So you'll have, we took a cross-section of the beam at 20 meters, and we'd show that the center point of it would be the original line trace, and then the divergence, we'd have radial circles around it. So we'd have points in a circle around the center point, and then the number of circles that we have is dependent on the previous radar scan and the distance we had from that. Hopefully that's clear. If not, I'll do my best to clear it up. But yeah, so we've now implemented the divergence, so we've discretized the beam so that we can get hit points from multiple different parts of the beam and combine that to give the result from the beam. And currently the power is split over that by a normal distribution. So we're taking the most power in the center and normally distributing it to the further points on the circle. And we have complete control over the number of points in each radial circle. So next steps. So just to recap what we currently have a model that detects objects. It can detect their width and their velocity. Some of this information we can get directly from the Unreal Engine. We've now converted that to work so that we can include the divergence, which gives us a better representation rather than a single line trace, and the power is normally distributed. What we're looking to do in the future is we're looking to adjust this output based on different types of interference. Hence why I was talking about the interference earlier, because with the two ratios we're talking about, interference with multiple radars on the road is going to severely affect our detection performance. So we're looking to model that, understand what the impact of it is, and implement that within our model. And like I said earlier, at some point we will be looking to do some measurements to improve the RCS calculation within the model. So just a final slide, just to summarize what the future of radar in automotive might look like. So as I've been saying, interference mitigation could be as important as detection performance because it directly impacts the detection performance. I've put this in here, this digital code modulation. It's something I've come across recently that could be massive, which is using a digital signal to change the phase modulation within your radar. So essentially it works by sending a series of zeros and ones, with a 0 representing a phase difference of 0, and 1 a difference of pi. And the benefit of doing that is you can do a lot better processing with digital information than you can with analog, so it might make it a lot more easier to do more with the radar itself. Higher frequency band, so currently most radar operate at about 77 gigahertz, but in the future we could see radar operating at 100 gigahertz plus, and the benefit of this is you get a lot better resolution, and you can be a lot more precise. Finally, something I've come across very recently is machine learning post-processing. So there is some work being done into looking at using machine learning algorithms to improve the detection of ghost targets. So machine learning algorithms can be quite good at differentiating between what is a real target and what is a ghost target. So this could be massive in actually identifying when we're having these problems and improve the object list we end up with. So that's everything. Apologies that all my figures disappeared, but thank you for listening. So yeah, thank you very much.